Okay, good morning, everyone. Thank you for joining me this morning. You can use the chat box to communicate with me. You can say just good morning, or you can, because I would like to check if you can hear me. I see good morning from Taren and from Jonathan. Oh, you can you hear me, right? Okay, great, excellent. That's what I want to check, because as always, I have to set up everything correctly. Okay, yeah, I see, because you can probably see I did log in twice, because as soon as I share the screen with you, I don't see the chat box. That means I have my additional monitor to see the chat box. Okay, that means we can start the second session in this week. I hope the first week went nice and smooth. It did, because I checked the first week assignments and everything looks good so far. I also checked the activity reports, and I would like to see a little bit more involvement, because some of the students, they don't really log in every day and not even every other day. And this is an online class. That means we have to be active, we have to be involved. That means please log in every day, please check something, do a little bit of homework, do a little bit of your reading, or suggested exercise, the extra exercise. You probably noticed I did add extra 2 modules. One of them includes the manual solution. That means you do have a solution for every single question in the textbook. I think you can use it smart. Of course, we don't want you to copy the solution. I mean, it's no point, but you can always check your solution against the textbook one. And I also add another module, which I think I call Practice with Kasia. I will always solve a little bit of problems, and I will make a short video, and I will post for you. That means this is the typical questions, which will correspond to the section that we cover. Because sometimes during the lecture, maybe we don't have enough time to practice more. That means I will always give you additional problems, and they are extremely helpful for your weekly assignments, and of course for midterm and the final. Okay, that's the small announcement from me. And yes, let's start. That means the second part of this week is section 6.6, and it's the inverse trigonometric functions. I will just check, this is the last section, right? Yes, this is the last section in chapter 6. That means I will introduce the inverse trigonometric function, and we will add a little bit of calculus, derivatives and integrals. And actually the integrals will be in our next 2 weeks, because chapter 7 covers lots of techniques of integration. That today we will finish with integration, which will be an introduction to chapter 7. Okay, do you have some questions to me? I mean, you can use the chat box. I'm looking at the chat box, and you can ask me anytime. It's just like we can treat this, even if it's recording, doesn't matter. We can treat this as a normal classroom time. Okay? That's what I want to mimic. Of course, I would like to see all of you, but this will be too chaotic. And I see more students attend this morning. That means thank you for filling out my doodle poll. I did pick 11 o'clock. Probably for the next few weeks, maybe I can try to change, because I really would like to accommodate lots of students. I can't accommodate everyone, because we do have different time zone, different, of course, schedule, but I will try to change a little bit. That means always watch the front page for the time, and I will always send an email and announcement. Yeah? What time will be my session? Maybe we can keep 11 a.m. Maybe that's good. Definitely 9 a.m. wasn't really a good choice. Okay, let's start. Trigonometric inverse. That means what we have. First of all, we remember from the very, very first section, 6.1, that function, in order to have an inverse, has to be, do you remember what's the most important property? Actually, I changed the slide by accident. You can read on the slide, function has to be one-to-one. And we remember what it is. For every single x value, we always have one y value, but the y value can't repeat. Okay? That's when we can't have two y values, of course, for different x's. That means geometrically, we can say function is strictly increasing or strictly decreasing. Okay? That means function must be one-to-one in order to have an inverse. And we probably know, let's look at the first function. I will uncover the whole slide. Okay, that means let's look at the first function, sine of x. That's the blue, yeah, that's the blue curve. And what do you think? Is this function one-to-one? Of course not. Thank you for answering. Of course not. Because, I mean, we can probably think about all of the trigonometric function. First of all, they are periodic functions. Yes, they repeat like every 2 pi, every 360 degrees. They repeat. That means how can we even think that they are like one-to-one? But what we will do, you probably know the mathematician, they are like crazy people. They know how important is the inverse, and especially for the trigonometric. That means they really want to define an inverse function for trigonometric. That means one of the ways is to restrict the domain. That means we will take just part of the sine function, and respectively for the other 5 trigonometric ratio, and we will create a one-to-one curve. And then we will flip it, let's say this way. That means theoretically, I can show this. Theoretically, we can take any part. Like let's say we can take from here to here. I can only take that part. Yeah, it is one-to-one. Or maybe I can take from here to here. It's also one-to-one. Or I can maybe take from here to here. It's one-to-one. But what we do have like a, because this will create lots of confusion. We have a setup. We did set up a certain domain, the certain like restrictions, constraint. That means for the sine function, we only gonna consider numbers from negative pi over 2 to positive pi over 2. Okay, that means I can show you that's the part of the sine that we will just look at and then create an inverse. That means please remember now the first information. As soon as we talk about the inverse trigonometric function, like in the inverse sine, we always thinking about this restriction. Only angles between negative pi over 2 to positive pi over 2, including the endpoints. And we can see this is the part, and it's definitely one-to-one. Great. That means now I can create an inverse. Inverse will be like, we know that inverse is symmetrical. I think something like that. That will be inverse, because inverse and function, it's symmetrical. My writing is sloppy. They are the mirror image to each other, and the line of symmetry is y equals to x. Okay, that means let's see. I will flip this. And what's happened? We do have a special notation to indicate an inverse. Of course, we know the -1 notation. That means, let's see. An inverse function of sine will be denoted by sine inverse. Yes, we can see sine inverse of x. Or we may also call ARCSINE. Okay? Because we know that in flipping like out, creating an inverse, the inverse sign, or saying the arc sign, will actually indicate the length of an arc to the corresponding angle, of course. Okay? That means to the corresponding angle, the inverse function represents if we will talk about the unit circle, the length of an arc. Okay? That's the reason that we call ARCSINE. And you can see that's the graph, a little bit nicer than on the previous slide. And another property of the inverse, we interchanging domain and range. That means the range was between -1 and 1. Now domain is between -1 and 1. And range was, we remember, I mean domain, the original domain was cut between negative pi over 2 and positive pi over 2. Now that's the output, that's the range. Okay, that means that's the notation, inverse sine of x or ARCSINE, depends what you prefer, the same equivalent meaning, and that's domain and that's range. Okay, that's we can see, that's how we dealing with the inverse. Okay, and that we have to really know the graph, and let's see. This is just the basic definition. You remember the inverse, the first section 6.1. I did solve some problems for you, and I said that's always the main algebra definition of the inverse. Okay? As soon as we're switching x and y, we will have this inverse notation. And the same for trigonometric. Let's maybe I can start reading from right-hand side. Sine of y equals to x if and only if inverse sine of x equals to y. That means as soon as I change the inputs and outputs, that's the inverse. And of course, the corresponding constraints. Okay, evaluate sine inverse of 1/2. Yeah, probably you know what it is, but let's see. I will say this is x, I don't know. Okay? Sine inverse of 1/2 is x. And then I can use my inverse notation. Sine of x equals to 1/2. Okay? That means sine for what angle is 1/2? Okay, now we have to really be confident with the unit circle. Do you remember? Can you tell me? It's pi over 6. Thank you, Robert. Pi over 6. That means this is the first quadrant. First quadrant, because sine is positive. And what will be the other solution? Because we also have the other quadrants that sine is positive. Yeah, like the reference angle. Do you remember in which quadrant sine is positive? In the first quadrant and the second quadrant. Yes, that means the second quadrant sine is positive. And this will be, yes, thank you, Karen, 5 pi over 6. But maybe I shouldn't write this. We have to be really careful. This one, we have to switch off the cameras. Okay. I will minimize this. This one, because we remember, this is not just the equation like that. This actually came from the inverse. That means I really have to make sure that my answer is taken from my domain, because that's the only set of numbers that I can pick my solution. And we can see this one is actually not. Okay, that's mean normally having this equation, we will have two solutions if we want the solution from 0 to 2 pi. But in this case, we can't. That means, please remember, we can't really accept this, only pi over 6. I know pi over 6 is still correct answer, but not in this case, not for the inverse. Okay, we can see that's the difference. Okay, let's try, because even if I will draw a sine function from, this is sine, this is not an inverse, because I do have that's my restriction. And we can see I want sine of x to be 1/2. That means 1/2, this is 1, this is -1, 1/2 is here. That means we only have one intersection. Pi over 6. If I will have my curve on the other side, I will have pi over 6. But it's only one solution, okay? Because we have this restriction. Okay, exercise number 2. Sine inverse, inverse sine of square root of 2 over 2. That means you probably know the answer right away. Sine for what angle is root 2 over 2? I can call x, I can switch. Sine of x is root 2 over 2. That means, can you tell me this answer? Sine for what angle is square root of 2 over 2? Oh, everybody can type. It's pi over 4. Thank you. Thank you, Jessie. Pi over 4. And this is fine. This is definitely between negative pi over 2 and positive pi over 2. And we don't have to take the second quadrant because second quadrant is not in the domain. Yes, only the first one and the fourth one. Okay, that means that's the only value. Yes, we will not repeat the same mistake that we did on the previous slide. Okay, that means you're okay with the domain and the values you need circle. Now, let's just try to find a limit. Normally, the limits are interesting when we're looking at the behavior of the function at the end of the domain. That means this is end of the domain, right? Because negative 1 and 1 is the end of the domain of the inverse function. That function is simply defined, and I can just substitute negative 1. That means, can you tell me sine for what angle is negative 1? Because I can say also, this is x, that maybe I can name y. And then sine of y is negative 1, if I would like to use my definition, but probably you know the answer right away. Sine for what angle is negative 1? For negative pi over 2. Yes, thank you. Oh, negative pi over 2, 90. Oh, not pi. Yes, yes. Pi is 0. Yeah, no, it's okay. And that means that you can always think the other way. Yes, sine for what angle is negative 1? Sine for what angle is root 2 over 2? Or any other values. Okay. And I think I have the graph. That we can see is just that point. Okay. Actually, just what I said that it's nice to investigate. Okay, Taren, yes, cosine. It's nice to investigate the end behavior. That means if function just ends at one single point, it's not really like fun, I mean, and we can still get the value. But we like when function goes maybe to infinity or negative infinity or some asymptote is involved, yes, then it's like a little bit more challenge, but we will get to that point. One of the trig function, the inverse trig function, behaves like that. Okay, oh, I did type the solution. Shall I erase this? Just not to have, sometimes I'm typing, sometimes not. Okay, that's me now, cosine. The same thing. I don't want to like repeat why we're doing this. You're probably confident now. We can't really take the entire cosine, of course, because the same periodic function, not really one-to-one, but we want to have the one-to-one function. That's mean in terms, I mean, with respect to cosine of x, this is the cut. That's the restriction from 0 to pi. Because if we will take from the same one, from negative pi over 2 to positive pi over 2, it's not really one-to-one. That means we can't really repeat the same domain as sine of x. Okay. That means the restriction for cosine is from 0 to pi. The range will stay the same, and we will flip this. You may probably notice this domain, it's positive numbers. Can you see? Only from 0 to pi. We're not including negative. That means if the domain includes positive numbers, then if I will create an inverse, the output, the range, it's going to be positive. The whole function will be placed above the x-axis. Okay. And we can even think about the line, the symmetry line, and how we will flip. We will flip this, oh, I believe like that. It looks like, yeah, it's symmetric. If we will close it with along the line of symmetry, I think I will match this. That we can see the whole function, the whole trigonometric inverse cosine will be placed above the x-axis. I can show you a nice graph. That's the graph. Okay. That's just, yeah, just one of the pattern. We know like mathematics is about patterns, connections, some formulas. Okay, the same notation, inverse cosine of x or arc cosine, because actually y, in this case y, represents the length of an arc to the corresponding angle. And that's the graph. we see the limitation. And please remember, always angles from 0 to pi only. If something is outside, always say not true. Always say we can't consider the other values. Especially watch the question like a true and false questions on the test. Okay, and let's practice. Cosine inverse at square root of 3 over 2. We don't know what it is. I will call x. Now I will switch. Cosine of x equals square root of 3 over 2. That means, can you tell me what's the angle that cosine is equal to square root of 3 over 2? For what angle? You remember the value? I think it's 30 degrees, Robert. Good. You know your unit circle, pi over 6. And this is the first quadrant. And the same thing. Cosine is, can you tell me which quadrant, what is the next quadrant that cosine is positive? It's the first one. And it's the fourth one. Thank you. But of course, can you tell me, you probably know that I will cross this solution, but can you tell me this value? Can you tell me the corresponding reference angle in fourth quadrant? Jonathan said 11, I think it is 11 pi over 6. Correct. Or, of course, we can use the negative. We can just, yes, get back 1 pi over 6, the same thing. But we, of course, know that we can't accept this because both of them are not placed between 0 and pi. This one is perfectly fine. That means normally we provide all of the solutions, but for the inverse, we only have to be in that range or domain if we're still thinking about cosine. Okay, so please remember, do not make this mistake. Okay, and the same thing, or I even have the graph. How inverse cosine behaves at -1. It's not really fun because domain ends at the finite number. We can see at -1, it's pi, because cosine at pi is -1, if we think about inverse. Okay, now this one. That's me. Now, I know we do have 6 trigonometric functions because we have 3 main ratio and then we have reciprocals. But for the inverse, we only want you to be confident with sine, cosine, and tangent. Okay? We will not really investigate the reciprocals, the inverse of the cotangent, cosecant, and secant. No, just sine, cosine, and tangent. Okay, tangent of x. We know that tangent is also a periodic function. Yes, we do have infinitely many of this shape. But we will cut the domain as expected. And the cut looks like that. We will just take exactly in the middle. We will take that part. That means domain, the restriction of the domain looks like we're taking an interval from -pi over 2 to +pi over 2. And can you see it's quite similar to sine function, sine of x. The only difference, can you actually see the difference? What's the difference between domain of the sine of x, the restriction of the domain of sine of x and tangent of x? Do you see the difference? This is for tangent, and for the sine, with excellent. We're not including the endpoints for tangent. We have an open parenthesis for tangent because it's the asymptote. We don't have the value at these asymptotes. But for sine, we're including the endpoints. I will erase because this is sine. Okay, and in this case, the range, it's all of the numbers. That's mean now we're gonna interchange this. Let's see. That's the inverse tangent of x, or the arctangent, the length of an arc for the corresponding angle. Okay, that means inverse tangent of x or arctangent, the same notation, and we can nicely see, I just flipped the function. Instead of vertical asymptotes, now we have horizontal asymptotes. domain becomes all of the numbers. Really nice. That means now the end behavior, the limit at positive infinity and negative infinity could be calculated. That's what I was saying. It's a little bit more fun than the finite numbers. Okay? That means the range is between negative pi over 2 to positive pi over 2, not including them. And range is, domain, all of the numbers. That means, let's see. That's what we have to know. If you see the limit of the inverse tangent at positive and negative infinity, we see the restriction. Value of the function as x getting bigger and bigger are never gonna be higher than pi over 2. Okay? If x is approaching negative infinity, the values are never gonna be lower than negative pi over 2. Okay? Two limits. And just, if we know the graph, they are quite obvious. Okay, that's me now. Let's see the quiz type question. Right? Still the limit, but of course corresponds to trigon inverse trig. Okay, find the limit as x approaches 2 from the right hand side, inverse tangent of the quantity 1 over x minus 2. Let me do the same thing that I did in chapter 1. I will name this t. Limit of inverse tangent of t. And t is approaching, I don't know. T is the behavior at 2 from the right hand side of this inner function, rational function. Do you think you can tell me that limit? If I will do the direct substitution, it's infinity, but we have to check if it's positive or negative. I think it's positive. Yes, I think you all right. That means we have 2 over 0. Of course, 1 over 0. 1 over small, of course, is big. We remember that always. But as soon as we see 0, we know that it's not really 0. It's not really 0 because this is not really 2. This is 2.1, or maybe even closer, 2.01. And this is tiny number but positive. Tiny number but positive. That means this is small number positive. 1 over small number positive is a big number positive. That means t. Oh, I didn't mean to delete my limit. As t goes to positive infinity, limit of inverse tangent at positive infinity. Do you know that limit? Who can tell me that box? It's pi over 2. Thank you. That's the new one. And I can even draw it. We do have a horizontal asymptote. My graph. Okay, this is exactly 0. Pi over 2, negative pi over 2. Okay, that means this is the limitation. Really good. But we can see we have to still compute the inner function and then the outer. Okay, let's see this one. Inverse tangent of natural log of x, and x is 0 from the right hand side. Right? That means how this function behaves at 0 from the right hand side. Do you remember how logarithmic function behaves at 0 from the right hand side? That's ln of x. And what is happening at 0 from the right hand side? You can type. Function is going down. Function is approaching big numbers. We can see big numbers, but negative. Negative infinity. And now this negative infinity is my t, my inner function, inner value. That means now let's think how inverse tangent behaves at negative infinity. Inverse tangent at t. This is t. We just did. That means how inverse tangent behaves at negative infinity. I can draw it maybe one more time. You can type, everybody can type, even if you're typing as a second person, it's still fine. I would like you to see it's negative pi over 2. Thank you. Okay, a little bit nicer. Negative pi over 2 is the limitation at positive infinity. Okay, that we can see the chapter, I mean the previous section in the week 1 information and week 2 information. Yeah, we can combine these things. Okay, now I do have some exercise. Okay, and let's try to evaluate this, or maybe simplify the same thing. Tangent of inverse sine of 1/3. Okay, that's what we have. We don't 1/3. I don't know. We like the 1/3. We like 1/2. We like square root of 2/2. We like root 3 over 2, but we don't really like 1/3. But what we can do, we can use some trigonometric identities, because we know we have lots of trigonometric identities. That's what I will do. In order to simplify, I will name this quantity y. And what I'm looking for tangent of y. Okay, that's me. Let's see. I said that inverse sine of 1/3 is y. I am using my definition of the inverse. I am interchanging. Sine of y is 1/3. I can do this. And you probably know, as soon as one trigonometric ratio for the same angle is given, we can get all of them. Sine, cosine, tangent, cotangent, secant, cosecant. Instead of maybe writing like trigonometric identities, we know that all of them are based on the right triangle. That means I'm drawing the right triangle as a tool, indicating angle y. And now, please tell me, if sine of y is the ratio of 1/3, we know that sine ratio in the right triangle is opposite over hypotenuse. Okay? That means I can say, what is the length of the opposite side? Can you help me? 1, thank you. And what's the length of the hypotenuse? It's of course 3. Thank you very much. Thank you, Robert. Thank you, Taren. And now, Pythagorean theorem. Do you think you can calculate the adjacent? If this is 1, this is 3, yes, we can use the Pythagorean theorem. Who can tell me? Square root of what number? Square root of 8. Oh, you even have the square root symbol. Okay, I like it. I don't know how can you type from the keyboard. Probably you have some shortcuts. Okay, that means this is 3 squared minus 1 squared, which of course is 8. We can simplify a little bit, 2 root 2, but square root of 8 is fine for now. Okay, that's me now. I have all of the sides, and who can tell me the final answer? Now we need tangent of y. What's the ratio for tangent in the right triangle? Having all of the sides. Do you remember? Tangent is which one? Opposite, adjacent, hypotenuse. Which sides? Oh, it's, yes, we can write this. It's opposite. Oh, it's opposite over adjacent. We can write this way. Or I can even simplify. Square root of 2/4. Please correct me. I did multiply, I rationalized the denominator. But even this answer is fine, because I just like to see the ratio. Okay? That we can see how we can deal with things like that. And we will need this triangle method a lot, and especially to finalize the integration. That's, please remember, you're probably gonna hear me, oh, do you remember the triangle method? That means that's the triangle method, okay? Okay. Okay, I have one more just to practice. Okay. Normally, if probably I will give you like 5 minutes and you will give me the answer, but let's see. You can try, maybe you can try to solve it on, if you have, I hope you have some notebook with you at the moment and the pencil, but I will also go through this. That means the same thing. Cosecant of inverse cosine of 3/5. I will name the inner function y. And I have cosecant of y. Inverse cosine of 3/5, it's y. then cosine of y, it's 3/5. Let's build a triangle, indicate the angle y, and who can tell me which side is 3, which side is 5? Which side is 3? Maybe let's do this way. Then you can answer step by step. Which side is 3? The opposite, or the adjacent, or the hypotenuse? The adjacent is 3, thank you, really good. And the hypotenuse is 5, thank you. Thank you, Jonathan, thank you for typing. Okay, that means this is 3, this is 5. Do you know what will be the length of the opposite? It's, of course, yes, 4, 3, 4, 5. That's our beautiful triangle, 3, 4, 5. Of course, we still calculated through the Pythagorean theorem. Okay, 3, 4, 5, excellent. Now I need cosecant. Cosecant is 1/sine, if that's easier. Oh, we don't really have to think. Yes, we'll be, okay, let's say, let's check. 5/4, I am just checking, because sine will be 4/5, 5/4. Very good. That we can see how quickly we can get the value. Of course, this is just the tool, because if the angles are a little bit bigger than 90, then we can still use it, but we have to be, we have to remember that it's just the tool. Normally, we will use the sine square plus cosine square is 1, or the other identities. But everything starts with the right triangle. That's the reason that we use it. Okay, let's keep moving. I will leave this one, it's similar. Okay, now let's look at the cancellation equation. We remember from the property of the inverse, when I make a composition of the inverse and the original function, always they cancel each other. I will always end up with x. And as we can see, sine, inverse, sine, x, sine, sine, inverse, x, and the same for cosine. But we have to remember this works, this is correct, if we keeping in mind our restriction. Okay, that means please remember we really have to keep the domain, the restriction for the domain. If the x value is from different interval, I mean from outside that interval, then it's false. Okay, then we can't really use it because we don't even have an inverse in this case. Okay, don't worry for this one. Yes, we don't really have to, you can check how this behaves, but they are way too complicated. We have domains, we will not really, I did type for you this one, but we not really, we don't have to remember and apply these functions. Okay, that's me. Now let's add a little bit of calculus. We know how they behave, we know the graphs, and we know that all of the curves that we just saw, they are continuous. They don't have discontinuity or asymptotes. That means they are definitely continuous function and no sharp corners, and they are differentiable. That means we can try to find the formula for the derivatives, okay? For all of them, sine inverse, cosine inverse, and the tangent inverse. Okay? That means 3 formulas new for us to remember and apply. That means we will start with sine. Let's see what I have. Okay, this is our function, inverse sine of x. Of course, we don't know what is the derivative. I have no idea. I don't really know. I can try to do maybe some slope of the tangent approach graphically. I can use the directly limit definition, but let's be a little bit smarter and use different way. Of course, that's the restriction, and this is function y, which depends on x. That's one of the notation, dy dx. Yes, I'm looking for the derivative of y with respect to x. That's what I did. I interchange, right, and I switch them. I kind of rewrite without an inverse. Sine of y is x. We know that this is true. Now, looking at my right-hand side of the screen, I have only sine function. I know what's the derivative of sine. That means I can take this equation and apply the implicit differentiation, which means differentiate like it is, and hopefully we will get the answer. That means I will differentiate still with respect to x, sine of y, the left-hand side, and x, the right-hand side. Of course, the right-hand side, what's the derivative of x? Can you tell me what's the derivative of x? Of course, it's 1. That means yes. Thank you, Jonathan. That means you will see 1 on this side. And now, who remembers from Calculus 1, what is the derivative of sine of y? Yes, y being the inner function, of course. It's cosine of y and times dy dx. Thank you very much, Robert. That's what we're doing. It's implicit, but we kind of follow the chain rule. I can write chain. Okay, dy dx, it's also, if you prefer not shorter notation, it's just y prime. But dy dx indicates better what is the independent variable, x, dx. Okay, now we're looking dy dx. I just solved this equation for dy dx. Dy dx, the derivative is just 1 over cosine of y. That means this looks okay. The only problem that I have, this derivative is in terms of y. And we can see my function is in terms of x. That means I really like to rewrite this. I have to rewrite the cosine of y, the y in terms of x. That means what we will do. Okay, I do have the final answer. Okay, that means I will write for you. Cosine of y, what is cosine of y? You may probably notice that we do have on that screen, we have sine of y given. Okay, that means sine of y is x. If I would like to see this as a ratio, I will write x over 1. And now, probably it's the first time, let's use the triangle method. I will build a triangle. I will indicate y, the angle y, yes, that's the angle y, and sine of y, it's x over 1, opposite over hypotenuse, right? If this is x, this is 1, this will be 1 minus x squared, okay? And now we just need cosine of that angle, cosine of y. And cosine of y is adjacent over hypotenuse, which I can skip the hypotenuse because it's 1. That's the final answer. Yeah, you can see how nice. Yeah, again, the triangle method. That means this is the first formula. Derivative of inverse sine of x, it's 1 over square root of 1 minus x squared. Excellent. And we can see even the domain makes sense. We can only accept the numbers between -1 and 1. And in this case, because this was domain, this was domain of the function, domain of the derivative, we can't accept endpoints because it happens that we have these values in the denominator. Okay? Yeah, but that's my point, the triangle method and this. Okay, please remember, we really have to know this formula. Try to memorize, but of course, not like memorize without thinking. We still have to think what we're doing. Okay, okay. Cosine. Let's do the same way. Differentiate cosine of y is equal to x. Differentiate cosine of y and differentiate x. X is 1. Derivative of cosine of y is negative sine of y dy dx. And I can solve for dy dx. Now what I need sine of y. Cosine of y is provided. Cosine of y is equal to, as a ratio, x over 1. X over 1. 1 minus x squared. That means sine of y, looking at this triangle, it's the opposite over hypotenuse. I can skip hypotenuse because it's 1. Excellent. That means derivative of inverse cosine of x, we can see is almost identical like cosine, like sine function, but we do have a negative. That means negative 1 over root 1 minus x squared quantity. Okay, one more formula, tangent. The same thing. Let's use the implicit differentiation. On the right-hand side, 1. Oh, I should ask you this. Maybe you didn't see. Do you remember the derivative of tangent? What's the derivative of tangent of y? Hopefully you didn't see this. I know that you did. But do you remember? It's important to remember sine, cosine, and also, yes, thank you for typing this, secant square of x. In our case, will be secant square of y, follow the chain rule, dy dx. And we will solve for dy dx. Also, I would like to say that we, of course, we have to know derivatives, but we will integrate a lot. That means also the integration will be helpful. Okay, that we have to be confident with the derivatives at first place. Okay, the same thing. I have 1 over secant square of y. I don't like y, but I know that tangent of y is x over 1. I will build my triangle. Can you tell me which side is x, which side is 1? I just want you to tell me. Yeah. And which one shall I put? What is the length of opposite? If I'm applying a tangent. Oh, everybody can try. We do have some participants. X is opposite, I believe it's correct, and adjacent, it's 1. Yeah? X over 1. Okay, that means if this is x, this is 1, this will be 1 plus x squared, square root. And we're just adding. Okay, and now we're looking for secant. That's secant. Oh, that's secant of y. Secant of y is simply 1 plus x squared square root over 1, but I will skip over 1. And secant square, I will just square the quantity. That means this is the third formula. Yeah? I don't know if you're making the notes, but remember, that's the third one. Inverse tangent of x, the derivative is 1 over 1 plus quantity squared, x squared. Okay? Nice and easy. So now, let's just practice. I think I have, yes, I have this, but again, do not worry for that part. Yes, we don't expect you to remember, but we really want you to remember these formulas. Okay? Inverse sine, inverse cosine, inverse tangent. But don't worry for this one. You can, yeah, it's nice to maybe know, yes. And if you would like to derive them, you can follow the same process, the same steps like I did for those functions. Okay, now let's see if we remember. Differentiate. Differentiate. It's my spelling wrong. Differentiate. Y equals to 1 over inverse sine of x. Right? Tricky function. Because I have to do this. This is inverse sine to the power of -1. But maybe I can write this. The blue -1 is a little bit different than this one, right? We know that. Because this -1 is just, it's not even -1, it's just the inverse. It's the notation for the inverse. This means the -1. This means the reciprocal. Exponent, the real, -1 as an exponent. Okay, that's what we have to do. We have to use the power rule and then the inner function, the chain rule. Let's differentiate. -1, quantity to the -2, and this is my quantity, and times derivative of this quantity. Let me put -1, quantity to the positive. Oh, no. Okay, that means instead of having a -2, I did place this in the denominator with +2. And now I need one more step. Who can tell me the derivative of inverse sine of x? Probably you can just type the formula. You don't worry for the square root. Yeah, you can type 1 over and what is in the denominator, because that's the new part. Okay. I did the chain. Yes, yes, you can write, oh yes, some of you are using beautifully the symbol, but it's the square root and 1, I see some mistakes, 1 minus x squared. Who typed, x squared minus 1, Jesse, no, Robert, and no, 1 plus x squared, but Jonathan, you're right, 1 minus x squared. I can come back here. You can see 1 minus x squared. Tangent is 1 plus x squared and no square root. Okay, that means 1 minus quantity squared. Okay. While I'm spelling, differentiate x times inverse tangent of root x. First of all, I see product. That means let's use the product rule. Derivative of x is 1 times inverse tangent plus x times derivative of inverse tangent of root x. Okay, I will copy this and I will copy. Okay, now we have to be really careful because we do have a chain rule involved. What's the derivative of inverse tangent? Who can tell me this? 1 over, and what is the quantity in the denominator? Inverse tangent has 1 plus quantity squared. And this quantity is that input. That means inverse tangent is 1 over 1 plus quantity squared times derivative of this quantity, because that's another chain. I mean, that's the chain rule. Okay, and let's simplify what we have. We do have inverse tangent plus, I will place that x on the top, square root of x squared is just x, and now derivative of the square root of x is 1 over 2 root x. Okay, and I can maybe leave it like that. I did simplify square of the square root of x is just x. I place that x on the top, and derivative of the square root of x, it's 1 over 2 square root of x. Okay. That we can see it's not easy. We have what we have. We do have product rule, we do have inverse tangent, and inside inverse tangent, a chain rule. Okay. Nice function. Okay, maybe one more. Oh, nice one. Inverse cosine of e to the 2x. So we also have an inner function. Okay. Derivative of inverse cosine is negative 1 over square root 1 minus quantity squared times derivative of this quantity. And this quantity is e to the 2x. E to the 2x. And we can see that's the always we have to put inside the inner function, always. Okay, negative 1. If I have e to the power of 2x and another 2, I can multiply 4x. And who can tell me this derivative? E to the 2x. What's the derivative? Do you remember from week 1? Exponential function? Yes, correct. Thank you, Jessie. It's the same function, e to the 2x times 2 times the derivative of the exponent. Really good. And I can place everything on the top, but let's just leave it. Okay. And now, let's see what we have. Now I will just try to reverse my differentiation formulas, and of course, I will get my integrals. That means seeing an integral of 1 over square root of 1 over square root of quantity 1 minus x squared dx. Okay? This is simply inverse sine of x plus the constant of integration. And why this is inverse sine of x? Because derivative of inverse sine of x is that expression. And the same for tangent. Integral of 1 over quantity squared plus 1 dx, it's always inverse tangent of x. That means, please remember, I think I said a few times, we will start chapter 7. We will have lots of different integrals.
as soon as you see denominator like that, you have to think, not always we will, because everything depends on the numerator also. But as soon as you see quantity squared plus 1 or even plus different constant, you have to think for a moment, oh, could be inverse tangent involved. Okay? That means, please remember, that's our job. We have to now pay attention what we have and what kind of integral it could be. Okay, one thing, I don't know, do you have some questions? Maybe I can ask this way. Do you have some questions to this integration? Do you think something is missing? Maybe one formula, or maybe this one? Do you think I can put different answer for this integral? What about if I will put negative? If I will put negative, I can answer negative sign, I mean inverse sign, but I can also answer this way. Do you agree with this? Because we know that the formulas, they were identical except the opposite sign. That means, yes, this is correct. If you see this integral, I mean this formula, we will just use some inverse sign. But if you will give me that answer, negative inverse cosine, it's still correct. We know we have the formulas before, but another proof is this, both of the functions, when I will draw them, they look identical, because everything, it's kind of like hidden in that constant. Let's maybe try. I will just show you, just to prove, but I can tell you inverse sine of x plus the constant is the sufficient answer. Okay, how was sine, inverse sine? Inverse sine, I think, looked like that. Negative pi over 2, positive pi over 2. Correct, right? Shall I? Okay, that's me now. What I would like to do, okay, that's my inverse sine. I just want to show you that it's the same function. Okay, maybe on this side, I know what I will do. I will draw, first of all, I will draw inverse cosine. Inverse cosine of x, I think, was like that, right? From pi to 0. Now, let me draw, I will use different color, negative. I will put negative. Negative means that I have to flip everything. Right? This is pi over 2. And we can see a little bit my scale, but we can see the blue graph looks almost the same like sine. But now, if I will shift down pi over 2 units, okay, I can use maybe different color. I'm gonna take this negative inverse cosine and shift down pi over 2 units. I will have the, now, this will be pi over. I will have this green graph. Negative pi over 2 and positive pi over 2. It's a little bit too tiny. I don't know why I'm squeezing on the corners, but that's my point. Negative inverse cosine of x minus a constant is the green graph. And the green graph is identical like this one. That we can see inverse sine of x plus the constant, whatever constant we picked, I picked this one, it's exactly the same like negative inverse cosine of x plus the constant. It's the same shape, the same slope, just shifted. That's when we can see, doesn't really matter what answer you will provide, it will be correct. But we will focus on sine. Okay, that means both of them are the same functions. Okay, let's integrate a few functions and we will be done for today. Okay, evaluate an integral from 0 to 1/4, 1 over square root of 1 minus 4x squared. That means what I see, I definitely see my new formula. Okay, I can see 1 over square root 1 minus quantity squared. But who can tell me what quantity squared I see? Because at this point, Yes, okay, it's 2x, really good. Because looking at 4x squared, it's not the whole quantity squared. This is the whole quantity squared. That means it looks like I have to use my u substitution. U will be 2x. du will be 2 dx. I can solve for dx in this case, and this is 1/2 du is dx. That means let's rewrite our integral in terms of u. 1 minus u squared. And dx is, I can place 1/2 du. Very good. 1/2. I can rewrite one more time. Okay, and what is this integral? Of course, is the new formula. It's just inverse sine of u.
Okay, what is missing? Normally I will replace u with 2x and put plus the constant, but we do have a limit of integration.
And you probably notice I didn't put the limits because
we need a new limits. Okay, if x is 0, then u is 2 times 0, of course is 0 too. That means now I can put 0, 0. If x was 1/4, u is 2 times 1/4. Yes, I'm just following that formula, which is 1/2.
1/2, 1/2. And now I can evaluate from 0 to 1/2. Let's try. Substituting upper limit, substituting lower limit. Okay. And you have to tell me inverse sine for, the other way. Sine for what angle is 1/2? Do you think you can tell me sine for what angle is 1/2? I can tell you this one is 0, is 0. Oh, I think we had this question today. Sine for what angle is 1/2? Pi over 6, yes, Robert, yes. Oh, pi over 7, yes, 6. I know, 6 is close to 7, next to 7 on the keyboard. Okay, that means the final answer is pi, yes,
close enough, I know.
Pi over 12. And that means we just multiplying by 1/2.
And that means this is really nice integral because it includes u substitution, new limits of integration, and the new formula. Okay, I have another one.
Actually, let me put 4
because I would like to show you something. Okay? It's integral of 1 over 4
plus x squared.
Okay? I mean, we know that as soon as we see like a constant plus x squared, we have to think, oh, inverse tangent.
But what we have? We have 4 and we don't like that 4. That means I'm gonna factor out 4. Okay, 1/4 will be outside.
And then I have 1 plus, and the similar thing. I have to see the whole quantity squared.
That means having x squared over 4, what quantity inside shall I put in order to have squared outside?
It's 1/2 x.
X over 2.
Excellent.
And now, the same thing.
I will let u to be that inner function. Du, it's 1/2 dx. 2 du is dx. Let's replace.
We have 1/4, 1 over 1 plus u squared. And we do have 2 du as a dx. 1/4 times 2 is 1/2. And integral of that function is simply inverse tangent of u. And I don't have limits of integration.
I will substitute back instead of u, x over 2. Okay, that means this is the way to actually manipulate the constant, which is not really part of the formula. But now what I want you to see the pattern. Yeah. You can always follow these steps and you can see it took maybe 2 minutes. It's not a problem, but it's always worth to know the pattern. Do you see that number?
It's 4, right? And let's see how that 4 affects the answer.
Because normally,
integral of 1 plus x squared is inverse tangent of x. That's no problem. Now we did have 4, and we can see I did divide x by 2 and multiply the whole function by 1/2. Okay? And I can tell you, if this, do I have, okay, let me just use that page. If I will have, or maybe I can use this one for now. Let's say this will be 9. Let's say this is 9. Do you think how the final answer will be affected? If that was 4, this is 2 and 2. If this is 9, this will be 3 and 3. Yes, it's 1/3. Thank you, Jessica. I know you probably were typing the same time. Okay, if this is 16, then what quantity shall I put in the denominators? If this is 16, it will be 4, always the square root. Or let's say this is 25, then we will have, yes, 5s. Okay, that means this is the general, let me write down somewhere, don't mess up our original. That's 4, 2, and 2. But I was gonna write this for you. If you will see a quantity squared plus x squared, I mean the constant, that A is affecting the formula this way. Okay? That means a squared plus x squared will always give you 1 over a and x over a. And of course the main formula. Okay? That's the way to remember. And as again, I said, because we will have lots of formulas. If you can follow the algebra steps, like the first 3-4 steps, it's still fine. You can still go step by step. If you remember this, it's also cool. Okay, let's solve the last one. Evaluate an integral from 0 to pi over 2, sine over x over 1 plus cosine square of x. So we can see it's tricky. But again, that's what I'm pointing out probably multiple times today. What I see in my denominator, I definitely see 1 plus quantity squared. Okay? Because that's always supposed to be for you the sign. Okay? That maybe inverse tangent is involved because we don't have square root. 1 plus quantity squared. Okay? That means I also see something on the top, but if you can think ahead just a few steps, the U substitution, probably we will need this to simplify. That means I will do the same thing. I will let U to be cosine of x. Du is derivative negative sine of x dx. That means I don't have negative, but sine of x dx is part of my integrand. Okay. I will remove this one. You will have this on the video. Okay. Now let's see. This is still good limits. Let's rewrite. 1 over 1 plus u squared, and sine of x dx is negative du. And now this is just negative inverse tangent of u. We need a new limits of integration. Right, but we can see that's how we can, again, we did recognize that quantity squared is in the denominator plus 1. Okay, new limits of integration. If x is 0, u is defined as a cosine of 0. Who can tell me this? If x is pi over 2, u is defined as a cosine at pi over 2. Okay, cosine at 0, Who can tell me that value? Oh, 1. Okay, good. That's mean 1, 1. And cosine at pi over 2? Cosine at 90 is 0. Thank you. That's we do have this. We can see I can flip the limits because I can remove the negative and I can put from 0 to 1. And you can see, please note, we don't have negative anymore because I did change the limits of integration. Maybe I can use blue color. And now looks normal from 0 to 1. Okay. Inverse tangent at 1 minus inverse tangent at 0. I can tell you this one, but you have to tell me this one. Tangent for what angle is 1? Okay, Jessica, it's fine, yes. Okay, can you tell me that answer now? It's yes, thank you. It's 45. That means the final answer, of course, is pi over 4. Also, this is really nice integral. I really like it because it's a little bit of challenge to realize denominator. Okay, thank you very much. That was the last question. Please, if of course the session is just here a little bit longer than an hour, but you can rewatch it. You can also you can always like try to focus just on the examples if you like. And I promise I will add some extra practice in the additional folder, practice with Kasia. Always check every single example. Then you're gonna be successful in this class. Thank you. Thank you.